We're continuing looking at different types of application problems here. This one again will eventually focus on a rational sort of function. But this is definitely geared more towards geometry. There are going to be some formulas in here that you've used in the past. I am not going to require you to memorize them, but you should understand how we can move things around and do substitution with this. The problem reads as follows. Stewart Cannery will package tomato juice in cylindrical cans that hold 2,000 cubic centimeters. Find the radius and height of the cans if the cans have a surface area of 1,000 centimeters squared. So you would need to know a few formulas from geometry. 2,000 cubic centimeters, that deals with volume. So the volume of a right cylinder is pi times r squared times h. So we would say that the volume that we currently have, 2,000, has to equal that formula. And then 1,000 is the surface area. For a cylinder, there's two parts to that. There is the base, which is pi r squared, and there's two of them. And then the formula for what we call the lateral area, or the side area of that cylinder, is the perimeter. So 2 times pi times r, the diameter really, times the height of this cylinder. So perimeter times height. Some of that might kind of sound familiar to you, but I'm sure it's been a while, so don't fret about that. You will be given those formulas. Okay, so our job is to figure out what the radius and height will be to fit these two situations. It has to have a volume of 2,000. It has to have a surface area of 1,000. And if you notice, these both have two variables. We really would like to have something that just has one variable, because then it's going to be a little bit easier to graph. So we need to kind of we need to pick one of these things and kind of move things around, solve for one variable, and then do some substitution, because that would allow us to combine the two into one and hopefully just have one variable. So I'm going to suggest that we would work with this one because there's just less parts to it. It's going to be, for example, very easy to solve for the h here. I would just divide by the pi r squared. Now I'm not quite sure what's going on with this. It seems like something funky happened with my program here, but still that's pi r squared. 2,000 over pi r squared would equal the height. Okay, same can, so h and r should stand for the same thing. So what I can do now that I've solved for h, I can take that and plug it into the h of the other equation. When I do that, I'm going to be left with just one variable, r, and that's going to allow me to do some graphing. So if I were to make that change, I get this. Now I could certainly simplify some things here. For example, 2 times 2,000 would get me 4,000. Pi and pi would cancel off, and this is an r that's kind of in the numerator. This is an r squared that's in the denominator, so some things would cancel off there. But you certainly could just graph it the way it is. You just have to be careful with some of the parentheses that you see. So maybe you would make y1 1,000, y2 this really complicated thing. You'd have to think a little bit about what would make sense for a window. You already know that y1 is 1,000, so that kind of tells you maybe go from 0 to 2,000 perhaps for your y range, so that this 1,000 is right in the middle. But then you have to think what realistically would be good values for the radius, and you're not going to have a radius that's in the hundreds. You know, it's going to be pretty small. So you set up your graph, or you set that up, you should get something like this. Again, the x value was your radius. The y values, your y-axis, one of the things you graphed was 1,000, which is your surface area. And so you see that there's two places where these graphs cross. So you need to find those intersections. One's at 4.62. One is at 9.65. So remember that x's stand for the radius that we're looking for. So the can overall that we are hoping for could have a radius of 4.62 or 9.65. We just need to think a little bit about maybe what the height would be. And so if you look back through your notes, you do remember that we had this equation at some point. It's that kind of converted volume formula. That is good for this can. So I can plug these radiuses into that formula and I get heights that correspond to them. So they have a couple options here. There are two cans that would fit their needs. They could pick a can that has a radius of 4.62 and a height of 30 centimeters. They could pick a can that has a radius of 9, almost 10, and a height of almost 7. And they could kind of figure out which one would fit their need better, but it would meet the requirements that they started this problem with. Okay, we'll stop there.